In this lecture, we will work out two examples that make use of the Coulomb's law that was presented in the previous lecture. So the first example is as follows. The average distance r between the electron and the proton in the hydrogen atom is 5.3 into 10 to the power minus 11. We are asked to calculate the average electrostatic force that exists between these two particles. And we are also asked to calculate the average gravitational force that exists between the two particles. So let's draw the hydrogen atom. This is the nucleus which contains a proton P, and then around it revolves the electron E minus, and the average distance between them is given by 5.3 into 10 to the power minus 11 meters. So this is the planetary model of the atom. To solve for part A, we will write the Coulomb's formula. So F of E, the force on the electron, is equal to 1 by 4 pi epsilon 0 Q1 Q2, where Q1 is the charge of the electron and Q2 is the charge of the proton. Since the charge of the electron and the charge of the proton is same, we can replace Q1 and Q2 by E square divided by the square of the distance between the two particles. Substituting the value of 1 by 4 pi epsilon naught, which is 8.99 into 10 to the power 9, and E square, where E is the charge of the electron, 1.6 into 10 to the power minus 19 square divided by R square, where R square is 5.3 into 10 to the power minus 11 square. If we simplify using a calculator, we get a force of 0.2 into 10 to the power minus 8 Newton. At the very outset, this force may seem very small, but remember that the mass of an electron is very, very small. So therefore, the acceleration that this produces is of the order of 10 to the power 23 meters per second square. We can use Newton's formula F equal to ma to calculate this acceleration. Now let us solve for part B. Part B says, what is the magnitude of the average gravitational force that exists between the proton and the electron? The average gravitational force Fg is given by G, mass of electron times mass of proton divided by R square. The capital G is the gravitational constant. Also notice the similarity between the gravitational force and the Coulomb's law. Both vary as 1 over R square. So let's substitute the value of capital G, which is 6.67 into 10 to the power minus 11, Newton meter square kg square. We will not put those here. Mass of the electron is 9.11 into 10 to the power minus 31 kgs. And the mass of the proton is 1.67 into 10 to the power minus 27 kgs. This whole thing is divided by 5.3 into 10 to the power minus 11 whole square. If we simplify this, we get a value of 3.6 into 10 to the power minus 47 Newton. Notice the huge difference between the electrostatic force of attraction and the gravitational force of attraction between the proton and the electron. You can roughly say that the force of attraction, electrostatic attraction, is at least of the order of 10 to the power 39 times the force of gravitation. So gravitational force is a very weak force. Let's go on to example number 2. Let me read out the statement of the problem. The nucleus of an iron atom has a radius of about 4 times 10 to the power minus 15 meters. And this nucleus of the iron atom contains 26 protons. What repulsive electrostatic force exists, or what repulsive electrostatic force acts between two protons inside the nucleus if they are separated by a distance of 1 radius? So as with many problems in physics, it is always better to draw a figure. So here we will imagine the nucleus of the iron atom to be a sphere whose radius is equal to 4 into 10 to the power minus 15 meters. And inside this sphere reside the protons. There are 26 protons. Since protons are positively charged, there is a force of repulsion between them. And we are asked to find this force of repulsion. Let's say one proton is here and another proton is at the center of this sphere. And the distance between these two protons is equal to r. To find this force of repulsion, once again we make use of Coulomb's law. F equal to 1 by 4 pi epsilon naught, which I abbreviate it as K, Q1, Q2. Q1 and Q2 is the charge of the electron. Therefore, I can write it as E square divided by R square. Substituting the values that have been given in the problem, 1 by 4 pi epsilon naught is 8.99 into 10 to the power 9. Charge of the electron is 1.6 into 10 to the power minus 15. And there is a square here, so square this value. Divided by 4 into 10 to the power minus 15 whole square. Simplifying this, we get a value of 14 newtons. This is a very large force. It is instructive to compare the force of attraction between a proton and an electron, which has been worked out in example 1, compared to the force of repulsion that exists between the two protons inside a nucleus. It is almost 10 to the power 9 times the force of attraction between a proton and an electron in an atom. Now, a natural question that any student can ask is, if there is a force of repulsion between protons inside a nucleus, how come the nucleus is stable? And the answer is, there is a stronger force of attraction called the strong force that keeps the nucleus stable. And in the early 1900s, people experimentally discovered that there is indeed a very short range attractive force that exists inside the nucleus, and this strong attractive force is the reason why the nucleus is stable. With these two examples, the current lecture is over. In the next lecture, we will look at the principle of superposition of electric forces, and we will work out an example.